On Thursday, be sure to come. If you want credit, it's only worth 12.5% of your grade, but I still suggest you come, take the test. So that's one thing. You know, I mentioned what you need a number 2 pencil, you need a calculator, 1 page of notes, single-sided, 8.5 by 11 inch. I think that's all you need. Okay? Any questions on it? There's going to be 10 multiple choice. And it will cover chapters 35, 36, and 39, up to the sections that we covered and the homework covered in class. Right? You will not be responsible for things that were not covered or not tested, not homework. Any questions? Yes?
The 1 page of notes, it has to be handwritten, right? Or it can be other.
You can type it, you can make it in Chinese, English, your favorite language, you can do whatever you want on it. You know? You can download your favorite pictures, whatever you want to do. Yeah.
It's a single-sided?
Single-sided.
Okay.
And your formulas are provided anyway, but it may make you feel better to have them in your form rather than my form. So, and I passed them out earlier, so you already know what formulas are going to be provided for you. Okay, are we ready to go, guys? Ready to go? Okay, we still have a lot to cover. Good. All right, so let's get started. Last time we talked about black body radiation. We talked about the fact that Max Planck made what we call the quantum hypothesis to explain the black body radiation. He assumed that the molecular oscillators, bipolar molecules going up and down, had their energy quantized. And then according to h times the frequency, in other words, the quantization of energy of an oscillator was equal to the energy of an oscillator was equal to h times the frequency of the oscillator, right? And for harmonic, for a bipolar molecule that is oscillating like two particles on a string, then we would say this was just 1/2 pi times the square root of k over m, or m over k. I can't remember if I wrote it down right. You can look it up. Okay, and then what Einstein did was say, yes, but it's also true that the energy of light is quantized. And the energy of light is quantized also as h times its frequency, where f is the frequency of radiation, and f here this is the mechanical frequency, right? This is the mechanical frequency of the oscillator. And this is the frequency of the radiation, right? And both of them are true. And we're going to use this property that light has its energy quantized in as h times the frequency of the radiation. And it consists of particles. So each particle of light is called a photon. So this is a photon, this refers to the energy per photon. And a photon is a particle of light. So we now have a dual picture of light. Sometimes it acts like a wave, sometimes it acts like a particle. Okay? That's called wave-particle duality. Sometimes light acts like a wave, like interference, diffraction, that sort of thing. That is the wave property. The particle property came about to explain the black body radiation. And Einstein was the first to propose this. And he then took that one step further and said, okay, let's suppose that the particle interpretation of light is correct. Let's suppose that this now represents the fundamental equation for the energy of a quantum of light. And that quantum of light is called the photon. So a wave is a continuous energy source, right? It has a velocity of motion Water waves can break a breaker or knock over, stones at multiple places because it's a distributed energy source. It has energy everywhere that the wave is located. It's continuous. The particle property, the energy is only localized at certain points. And those points are where the photon carries the energy, and it's called a packet. Right? So now, instead of having continuous energy, like a wave, they come in discrete packets of energy. Right? And each one of those packets is called a photon, and each photon carries energy that's equal to h times the frequency of that wave. So it inherently uses the wave property of the frequency to calculate the energy property of the photon associated with that wave. Stop, think about that a second. Any questions? Okay. Does what I just said make sense? You're free to shake no, but does this make sense? Light is sometimes acting like a particle, sometimes it's acting like a wave. In the case of black body radiation, we describe it as a particle phenomenon. And we're going to show that the particle phenomenon is also true for the photoelectric effect, which was the next step. Okay, so think this. So Einstein proposed the idea and said he came up with this through the black body radiation experiment, and he said if what I am proposing is true, and light does in fact behave like a particle, and my fundamental assumption that I used for black body radiation is correct, let me propose an experiment to verify, to test that hypothesis. And I'm going to propose an experiment that is the following. I take a light source, so I have light of, let's say, wavelength lambda, right, which we said can be written as c divided by the frequency. And we're also going to use the quantum hypothesis that the energy of the photon, which I'm going to denote as gamma. A little gamma here is my way I denote a photon. Notice that in the energy term I have E, that denotes an electron. But for a photon, this is h times the frequency of the radiation. Okay? Okay, so his idea was, if I shine light onto a metallic conducting surface, so this is light, and I shine it onto a conductive surface, then I should be able to knock out some electrons as a result of that. Okay? And if my hypothesis is correct, then there's a very simple energy equation that's going to explain how this kinetic energy, which is generated from the absorption of light, is related to the energy of the photon. And it's a conservation of energy principle. So the statement of conservation of energy is that we're going to say that h times the frequency is the incident energy, and when it gets absorbed, then I do two things. First, I have to knock out an electron. That requires some energy, because as we know, electrons are bound in orbits, right? So there's a binding energy that has to be overcome. So the first thing it's going to do is some of that energy has to go into overcoming the binding energy. So this will be enough to, we will say, to liberate the electron from the surface, right? Liberate the electron. And then the remainder of the energy can go into the kinetic energy of the electron. So I get that the energy that's being provided by the light is equal to the binding energy holding the electron in the orbit that has to be dislodged. That requires some force or some energy. And then the remainder of that will be converted to kinetic energy, or classically we call it 1/2 mv squared. So he proposed this energy equation. Now, first of all, or next of all, I should say, what's going to happen here is that the way we detect this is that we produce this system in a closed container, which we will say is a glass tube, for example, and which is evacuated because we don't want any air contamination. We want to measure the electrons liberated from the cathode and arriving to the anode. So we apply a bias voltage here. So this is some voltage V, right, that we apply. Over here is an ammeter that measures some current I. And as a result, when I turn the light on, electrons are ejected from the surface, and I now get current that is flowing through the loop. The current is going around this way, right? The electrons are flowing this way. The current goes opposite. But I get this, and so I will get a reading on the ammeter, right? The ammeter is going to register some current. If I turn the light source off, the ammeter reading goes to 0. Turn it on, I get current. Turn it off, I get nothing. Turn it on, I get current. Turn it off, I get nothing. So this light source now is providing a way to generate a current, okay? And according to Einstein, this should be given by this equation. So this light consists of packets of energy, which I will show by dots, and one dot at a time, one photon at a time, hits the surface, one electron comes off. So photon in, electron out. Okay. Right, everyone follow me so far? Okay, photon in, electron out. Okay, so that's one thing that I can do, and that is a device that was actually confirmed, but that's not the whole picture of what this is about. Now, the second part of it is that if we look at the theory of atoms as we know them, then we know that an atom consists of a nucleus with a positive charge, we call it plus Z. That's called the atomic number. I have electrons in orbits that are going around here. And depending on which orbit the photon, the light, hits, the energy of the ejected electron will be different. So in other words, when I write this symbol down, that what's happening here is the electron is getting ejected from the atom. Right? And it's going to take more energy to knock out these inner electrons than it does the outer electrons. The outer electrons are called valence, and valence electrons are loosely bound. So these are loose bound. Okay? The valence electrons are loose bound, and they require the least energy to liberate the electron. Okay? So we're going to have a special name for that. So the minimum binding energy, and now I'll spell it out, energy, is the least energy to ionize the atom. The least energy required to ionize the atom. Okay, everyone clear about that? If it hits an electron deep into the inner orbits, these things are more tightly bound. The valence electrons are loosely bound. So for the valence electrons, there's a special name for that. By the way, let me try to draw it. We messed up the writing a little bit. Loosely bound. Right? There's a special name for this loose, this loose bound. This is the one that has minimum binding energy. That's this one right here, is the least energy. And there's a special name for that. We call that the work function. This is equal to the work function. Okay. Try to write this a little bit better. This is equal to the work function. And it's unique for every different type of material. It's different if it's copper or it's aluminum or it's magnesium, whatever the material is, it's unique, right? Because every element has a unique binding energy and valence structure for their electrons. But the minimum energy is the least. So for those interactions, for those ones, and that's the one where I am now ionizing on the valence, the outer ones right here, this electron energy is going to be a maximum. Okay? Because if the binding energy is a minimum, this number is fixed, the kinetic energy is a maximum. Okay? So I can rewrite this and say that the maximum kinetic energy that's acquired by the electron is equal to h times the frequency minus the binding energy, or in this case, it's the work function, which we call W. I don't know why they call these letters. I'm not sure the origin of the names, but it's important that you understand it's the minimum energy required to ionize, which is coming from the valence, ejection of a valence electron, because it's the most loosely bound. Therefore, it will have the greatest reserve remainderment of energy that can be imparted to the electron. Right? And as we said, this is kinetic energy. Okay, so so this is the equation. Now, the question is, how do I measure this quantity, E max? So how to measure EK electron max? I could have written this differently, but I chose this way of doing it. Okay, how do we measure that? Well, the way we're going to measure that is to provide a reverse bias here with a variable voltage supply. So let me write it a different way now. Let's suppose that I'm now going to put the negative terminal of the battery on this side. So this side is negative with respect to this side of the battery, which is positive. And let's say we start out at 1 volt. Right? 1 volt is the bias that is on there. Let's suppose that the maximum kinetic energy is 10 electron volts. So let's suppose that, I'm not sure the best way to write this. Let's suppose that EK electron max is equal to 10 electron volts. Right? By the way, I do know how to calculate a velocity for this particle. Right? This, if I want to know the velocity, this is totally a side note. We did review some equations of kinematics. This is 1/2 m times MEC squared times beta squared. And this number is 511,000. Excuse me. This number that we said was the mass energy of the electron is 511,000 electron volts. And so it turns out that beta is equal to 0.006 times C. Right? I can solve that. Put in the numbers. Anyway, just something to keep you refresh on your memory of kinematics, right? The energy in electron volts can be converted to a velocity. Okay, so that's one thing. So suppose I have this energy, and suppose I start off with 1 volt. Well, what's going to happen here? The electron is going to lose 1 volt of, it's going to overcome a barrier of 1 volt of potential to get from this electrode over to this one. So by the time it arrives over here, then it will have 9 electron volts of energy. Okay? It's going to have less energy. It's a reverse bias. It's slowing it down. So if it started with 10 electron volts here and had a 1 volt reverse bias, retarding it, then by the time he gets here, it's going to be 10 minus 1 is 9 electron volts. Now I raise this up to 2 volts. 2 volts, the 10 electron volt maximum energy. Remember, there's a whole bunch at lower energies, but this is the maximum. Right? This is the maximum. And I want to find a way to measure the maximum. That's what I'm after. So I raise this up to 2 volts, and now the most energetic electron has 8 electron volts when it gets across here. All right. Finally, I raise it up to 10.01. Or let's say I raise it up to 9.99 volts. Then it still has a little bit of energy, and it's going to make it across over to the other side. But as soon as I raise the voltage up to 10.01 volts, now this guy with, we start out, we're going to assume that its maximum is 10 electron volts, right? No longer has enough kinetic energy to overcome the barrier of a voltage that's larger than 10. So what happens is the electron makes it almost the way over here, it turns around and stops. That's the most energetic electron. All the lower energies have also been turned around and stopped because they had even less energy to start with, and they couldn't overcome that potential barrier. So at a critical point in this voltage, the current stops. So I increase V until the ammeter reads 0. I equals 0 on the ammeter. And I call that the stopping voltage. So that is equal to the V stop. And that's the voltage I need to stop the most energetic electron from getting across. Okay. And therefore, I know that because of that, then the, let me see if I get this right, that the maximum kinetic energy of that electron was equal to 10 eV. Okay. So if I've now found a way to determine what is the energy of the most energetic electron. It's the voltage that is required to stop the current completely, which is just high enough to stop the current completely, when multiplied by E, the charged electron, is the energy in electron volts that the particle had. So that tells me what was the kinetic energy when it left the surface. I applied just enough reverse bias so that the most energetic electron cannot make it across. Is it clearer than mud? Yes.
So if you increase your voltage from your battery, so your I used.
Are you decreasing or increasing this voltage?
So if you increase your voltage,
yes,
you're going to have a stronger light source to have the electrons flow across the graph. Is that right?
No. Well, classically that's true. Yes.
Okay.
The classical picture is if I increase the intensity of the light, I get more energy of this electron. And how do I increase intensity? I increase the amplitude of the electric field. Right? That's going to be on your test Thursday, so make sure you know that. Intensity is proportional to the square of the electric field amplitude. Okay, so yes, that in fact should be true. But in fact, what this says is that it doesn't depend on intensity, it depends on frequency. What happens if I increase the intensity is I flood this with more photons, but the energy per photon doesn't change. Right? So that's another thing, is that increasing intensity, so if I increase intensity, then what happens? Well, classically speaking, in a classical system, the wave theory, right? The classical theory of light is wave. So let's call this the wave theory. Increased intensity from the wave theory. Then I increase 1/2 epsilon naught times the square of the electric field amplitude. This is what we call the S vector, or the intensity in watts per square meter, right? And you're right, if I increase the intensity, I should be providing more energy to get the electron, get more energy out. But it doesn't happen. What happens is, it doesn't change the maximum energy at all. What it changes is the number of electrons I get off the surface. Okay. So let me refresh. So for the wave theory, and this would say that EK electron max increases with intensity. It increases with intensity. Right? According to the photon picture, which we call the particle theory, the particle slash photon theory, the energy per photon, we have H times F is the energy per photon, and the intensity, or I, what I will call I, is the number of photons, per square meter. Okay? This is the particle picture. Both of these represent an energy density in watts per meter squared. By the way, this should probably be energy per photon per second, but per second. Okay, but they are totally different pictures. What we know experimentally is that increasing the intensity, okay, this is proved to be wrong. So what we say right here is this is not true. This is false, right? That increasing the intensity does not change the maximum energy, but it does change the number of electrons leaving the surface. Okay, so this notion is proved false, the classical picture, and Einstein's notion is proved correct. So Einstein's notion is, this is the equation that we want to use to describe the maximum, or this equation is the one we want to use to describe the maximum kinetic energy. Okay. So we now have a way of measuring this, right? We said that what I can do to make this measurement for every frequency, this quantity right here is equal to the stopping voltage times the charge of the electron. So this maximum is the stopping voltage, V stop, times the charge of the electron. That is a measurement of the maximum kinetic energy that's released from the surface. Okay. This is how you measure it. I crank up this voltage from 1 volt up to 10 in this case until the ammeter reads 0. Okay. That defines the maximum kinetic energy of the electron. Assuming this is a vacuum, of course. Well, yeah. Yeah, assuming everything is in vacuum. That's what we used to call a vacuum tube, a glass tube that's where the air has been pumped out. Okay, any questions on this so far? I don't know if you're just trying to make me go slower so I don't cover more material, or or there's really something like that doesn't quite make sense. Okay, so this is the equation we have. Okay, so now we can use this now to make a measurement well, we can to correlate frequency with maximum kinetic energy. Right? So what I'm going to do then is to make a plot of the stopping voltage versus the frequency. So I know how to make different frequencies of light. By the way, do I have a black pen? Yes. I know how to make different frequencies of light, and we do that with different types of light sources. But the plot that we're making is that we're going to look at is the stopping voltage, V stop, versus the frequency of the light. Frequency of light. Okay? And what we find experimentally is that the stopping voltage is 0 up to some critical value, which is, we'll say right here, and then it begins to increase linearly. Okay? And furthermore, this is independent of intensity. This curve is independent of the light intensity. So in other words, no matter how intense I make this light down here, which might be enough to burn your eyesight completely, that unless it reaches a threshold value of the frequency, no light comes off the surface. But once you are at a frequency above that, then the electrons, then this process starts happening, and electrons start coming off. Okay? And when they come off, there will be some maximum voltage or energy that they will be coming off with, and I can measure this. So now what I do is I solve this equation for V stop equal to H over E times F minus W over E. By the way, in the books you'll probably see this as W sub 0. This W usually has a 0 on here like this. And so I need to put that in here as well, right here. Okay? And this is the equation we have. Okay? So imagine that these are like 5 data points. In fact, if you were in the 284 lab this year or before, you would have actually done this experiment. You would do 5 different frequencies, you would measure 5 different stopping voltages, and you fit it to a straight line. Okay. If you fit it to a straight line, then the slope is equal to H over E, right? Where E is the charge of the electron. Right? So I do the experiment, I find out the slope, and now I can say that E, which is equal to 1.6 times 10 to the minus 19 coulombs, when multiplied by the slope, so E times the slope is equal to H, and I get that this is 4.14 times 10 to the minus 15, EV seconds. And I have now found a new way to measure Planck's constant. Right? Surprisingly, it turned out to be exactly the same as we calculated H from the black body radiation. That means there must be something real taking place, that this equation, E equals H times the frequency, is really happening. This isn't just a fluke of a single experiment that it fit the data, and if I assume that light acts like a particle and has this frequency, that I can explain one experiment. I can now explain 2 experiments. Right? And soon you'll find that we'll explain 3, 4, and 5 experiments. Right? So at some point you say this is real. This becomes real. And so this is what we get. Right? So that was remarkable. For this, Einstein got the Nobel Prize in physics, not for relativity. That, and of course, the work on the black body radiation, which was really quite the difficult task at the time. Max Planck read his paper, realized how brilliant he was, and decided to hire him to work in Berlin in his physics institute while he continued to work on the general theory of relativity and the new theory of gravity for 10 years. But anyway, that's a different story. But yeah, this is what he got the Nobel Prize for. Now, let me ask you a question. How many of you know the experiment in which this constant of the electron was measured? How many of you know the experiment that determined this value for the charge of the electron? Okay, I absolutely expect. I mean, I'm not shocked. I mean, I wish you had gotten this point in 273 because you did electricity, and one of the most important parts of electricity is the charged electron. It happened to be from what's called the milk and oil drop experiment. And I'm not going to go into too much detail about it, but basically imagine that you have a spray of fine oil drops coming down from the top of a chamber. And as the drops come through, there's a frictional rub that deposits some excess electrons on the drop, right? And you can measure the charge, whether it was 1 electron, 2 electrons, or 3 electrons, by finding out how much electric field, let's say you know the mass of the drop, right? The mass falls under gravity, you apply electric field in the opposite direction, and you can suspend it, right? You can balance the forces that gravity is equal to the electrical force upward, and from that I can determine how much charge is on the drop. I do that for 1,000 different drops. And all of them had a number which was this times some multiple integer number. So this was the common denominator of all the drops. You might get 1.6 10 to the minus 19, you might get 3.2 times 10 to the minus 19, you might get 4.8 times 10 to the minus 19, you might get 6.4 times 10 to the minus 19. But they were all integer multiples of this number. Therefore, the smallest possible charge that we can determine or measure was one that had exactly this number, because there was no charge on a drop that was smaller than this number. And every other drop had an integer multiple of that. So the charge is quantized, and the electrons didn't carry it. Okay, at least I got to tell you a little bit about that, which I think is very important. But yeah, that was a Nobel Prize as well. Called the Millikan. You can look it up on Wikipedia. It's called the Millikan oil drop experiment. Millikan. I can't remember how to spell Millikan. Millikan? I can't remember. I'm sorry, I'm gonna have to look this. Well, you can do your own search. Millikan. I know his first name was Robert. Millikan oil drop experiment. Anybody know how to spell Millikan? There's actually a university. I-K what? E-N. M-L-L-I-K-E-N. Yeah, that looks right. The Millikan oil drop experiment. Yeah. And that was important. Anyway, once we know that, then I can take this slope, multiply by E, and I can solve for Planck's constant. That was the goal of the story. Okay. So, make sure I didn't leave something out here. Any other questions on that? It's a departure from classical theory. This is the classical prediction, this is the particle prediction. Sometimes light acts like a particle, and sometimes it acts like a wave. And depending on the experiment, it will be one or the other. Okay? I cannot explain this experiment with the wave property, and I cannot explain diffraction with the particle property. So sometimes I have to go, oh, I'm looking at the particle property of light. And then sometimes I go, no, I'm looking at the wave property. So your mind has to switch. Which property am I looking at? Okay. Okay. Great. Okay. So now we're ready for the next step, which is Compton scattering. So this was done around 1905. Around the time of 1920, a physicist by the name of Arthur Compton began to investigate the scattering of light by electrons. And I'll draw this out for you. So we're going to talk about Compton scattering. Compton scattering. And it continued to build on the particle property of light. Compton scattering. We call it the photon picture or view of light. And the picture that we're looking at, what Compton did was to consider the following case. Supposing I have X-rays that are basically also electromagnetic radiation. We said that they are very short wavelengths. Remember, they are measured in tenths or hundredths of a nanometer, and light is wavelengths of about 500 nanometers, right? So there's 10,000 times shorter wavelengths than visible light, right? As a result, we also now know that because that means that the frequency is 10,000 times higher, that the energy per photon is going to be much larger for X-rays than it is for visible light, which is why X-rays are dangerous to our health. They are more damaging because they carry much more energy. To give us a scale, by the way, in terms of energy, the energy of visible light, the energy of the photon, let's say the energy sub gamma for visible light, is roughly equal to Planck's constant, 4.14 times 10 to the minus 15, times 10 to the minus 15, times 10 to the minus 15 eV seconds, times the frequency of visible light, which is about 5 times 10 to the 14th hertz, which is hertz. Hertz is cycles per second. Everyone familiar with hertz? Cycles per second. All right, so this comes out to be about 2 electron volts. Right? If I'm talking about X-rays, the energy of a photon for X-rays, and if I were to assume that that this is about 10,000 times larger, or that the wavelength is about 10,000 times shorter, then X-rays, this becomes 4.14 times 10 to the minus 15 eV seconds times 5 times 10 to the 18th hertz. Assume that it's 10,000 times larger, so this becomes 20 keV. Okay, so photon energies are measured in keV. Visible light photons are measured in eV, single eV. This has helped to give you an idea of scale between X-rays and light. Same electromagnetic phenomena. It's still an electric field oscillating through in space, but from the picture, from the particle point of view, they have much different energies associated with them. And this is, of course, the reason why X-rays are much more damaging to the skin and to the organs than visible light. You can stand in visible light almost all day long. Worst happens, you get some sunburn at the beach. You do the same thing with an X-ray beam and you die. So we know they're much worse. Yeah.
For the X-rays that say 5 times 10 to the
18th. Yeah, so I just picked, by the way, so I'm giving you an example here to kind of give you an idea of the scale. This is 18, this one is 14. And I multiply by Planck's constant so I can give you the energy of the photon. Okay? For X-rays and visible light. Okay? Any other questions? Okay, so back to Compton. So Compton was doing an experiment with X-rays, and so again, they have some wavelength lambda associated with them. And so I can also write that the energy of the photon for the X-ray is equal to HF, or I can write this as H times C over lambda. Right? HC over lambda is just, I'm just replacing the frequency with C over lambda. Another way of converting from wavelength to photon energy. Okay. So his idea was, if in fact light acts like a particle, so I'm going to put my little dots here now. Each one of those is a photon. And at some point on the surface of a very thin a foil, which, you know, I'm not sure the one he used, but we could say, for example, aluminum, that there's a loosely bound electron that is at rest. Now, electrons we don't really know are at rest, but they're in their orbits and associated with an atom. But if that kinetic energy is very small compared to what's about to hit it, then we can take this as being at rest. And so we take a condition where the initial electron energy, kinetic energy, initial is equal to 0. Right? So the initial kinetic energy of the electron is 0, and this X-ray knocks on the electron, and the electron recoils with some kinetic energy over here. This was the electron kinetic energy. And the photon scatters, but it comes off with a different wavelength, lambda prime. Why? Because it gave up some of its energy to the electron. And since the energy is given, has to be conserved, then it must have come off with a longer wavelength than it started out with. Because the energy of this final state, so I can say E gamma prime, is also equal to HC over lambda prime. Okay. Let's see what else I can do here. What else can I do? Okay, so one equation I can write down immediately is the energy equation, and the energy what am I trying to do here? I'm trying to set up an experiment where I can change, for example, one parameter. Let's say, for example, I have a light, an X-ray detector that moves at different angles here, and I want to know what's changing with angles. So, in other words, let's suppose I define a scattering angle phi for the photon, and I'm going to define another angle, which is theta, for the electron. So you have to keep in mind that phi is the photon angle, and it is measured with respect to the incident beam direction. So this is the incident beam direction, this is the incident direction, and there is a scattering angle scattering angle for the scattered photon, and there is a recoil. This is called the electron recoil. Electron recoil. Okay. So this is the picture that we want, and we want to use energy conservation to basically test, is this picture or this equation correct in explaining the scattering of this photon off of this X-ray off of an electron? Okay. So by the way, this electron might actually be part of aluminum or a very, very small thin foil that the beam can easily pass through, but we basically make an experiment that does exactly like this. Okay, now the equation of energy conservation, so we want to relate these variables and see if there's some correlation that we can measure. In other words, if I measure the energy of the scattered photon, how is it related to the angle? Or if I measure the angle of the electron, how is it related to the angle of the scattered photon? What's the kinematics that allows me to describe the complete process? It would be like, for example, if I had a billiard ball collision, okay? And I asked you, I said there was a billiard ball at rest, and we'll call that the 8-ball, and I have a cue ball right here, and I now want to ask you, if this angle recoils at an angle phi, what is the angle of recoil of the billiard ball? So the cue ball goes here, right? And the 8-ball goes over here. And I want you to describe this process. I can use conservation of energy and momentum to describe the scattering process. Okay? And so that's what I want to do here. I want to be able to make an experiment where if I know one of these variables, I can predict what the other one is going to be. And I can only do that if I can write down a conservation equation to solve for these different variables. Okay? So the equation that we have, first of all, is the energy equation. So the energy equation states that, like we just said, the incident energy, hc over lambda, is equal to hc over lambda prime. So this is the energy of the incident X-ray. This is the energy of the scattered X-ray, and this is the kinetic energy of the electron. Okay? So this is one equation that I have. I have the conservation of energy, which is exactly what I did up here. This one in photoelectric effect was also conservation of energy. Okay? So I'm using conservation. The energy that I have before has to be equal to the energy I have after the collision, after the event. Okay, so this is what I have before, this is what I have afterwards. Right? Now I also have X component, piece of X, conservation. And I have another one which is piece of Y, conservation. And what is X and Y? Well, I'm going to define this as the x-axis, and the direction perpendicular to the beam is going to be the y-axis. Right? And the momentum conservation has to hold for every component of momentum. In other words, if the vector p is conserved, that means that each of the components is conserved. That's to say that the x component before the collision is equal to the x component after the collision. Now there's one more big item I have to include here, which is a new expression for the photon momentum. Notice right here what we have written down is the photon energy, the photon momentum. Well, there's two ways I can get that. Remember that from the relativistic equation, we derive that the energy squared of the particle is equal to p squared c squared plus m naught squared c to the fourth. Right? So what is the mass of the photon? Well, if the rest mass of the photon is not zero, then it must be that the moving mass, which is moving at the speed of light, is infinite. Right? It becomes infinite because for a photon, V is equal to C. And I'm certainly convinced that any light beam that I have has finite amount of energy. Right? So the mass of the photon must be equal to zero. Okay? If I do that, then this equation becomes that the energy of the photon is equal to the momentum of the photon times the speed of light, c. Now there's another reason why I can believe that that's a true statement, because if you derive the classical expression in a wave for the energy of an electromagnetic wave, that wave also has momentum. A classical wave of light hitting a mirror will deflect the mirror. The light beam, the laser pulse, hits the mirror and the mirror responds. the light beam has momentum, right? It has momentum because it can knock a massive object away. So this does have, the light beam does have momentum, it just doesn't have any mass. So we don't use MV. We use this expression for, if you want to know what the momentum of it is, then what I'm going to do is, I got your question, just hold 1 second. What I'm going to do then is to put in, say this says that hc over lambda is equal to p of the photon times c. So the momentum of the photon is equal to h over lambda. So just like the energy of the photon is h times the frequency, the momentum of the photon is h divided by the wavelength. So I have a new way to relate the momentum of a photon in terms of the wavelength of the classical electromagnetic wave. Right? But I'm switching here, this is the lambda from the wave picture of light to the momentum of the particle picture of light. And the same thing is true here, E equals h nu. This is the energy of the particle of light derived from the frequency of the wave property of light. It's a little confusing because we have a wave and a particle that are operating in the same space at the same time. But you know, I either have to look at it from the wave view or I look at it from the particle view. But I can't look at it from both for the same for a given experiment. Any question on that before I go on? Yeah.
Why was the mass 0?
What mass 0? Okay. Suppose the mass is not 0. Then the moving mass has to be infinite. But that's exactly what I'm observing. A photon is going at the velocity v equals c, so the denominator goes to 0. That means that the energy of the photon is infinite. And there is no infinite energy light beam. So this has to be a wrong equation. Or I can say, I get this result, as a result, using this equation, I get E equals PC, and by the way, I can also derive this from classical theory of light. This is also true for waves. This can be the energy density of a wave, such as what I've drawn up here somewhere, 1/2 epsilon naught, that's the energy density of the wave. Or it could be, by the way, there's probably a factor C missing here, I can't. I think there's a factor C missing. Yeah, factor C missing there. Or I get the energy density of the light and I can relate it to the momentum of the light. It does become the same equation classically as quantum mechanics, or classically as the photon picture predicts. Okay. Okay, so now we're ready to write down momentum conservation. Okay, momentum conservation, okay. So now I have an expression for the momentum of the photon. It's h over lambda. So px conservation. Initially, the photon has a momentum h divided by lambda, right? That's the incident X-ray wavelength. H over lambda is equal to h, the x component of the scattered photon momentum is h over lambda prime times cosine of phi, plus the momentum, the x component of momentum of the scattered electron. So notice right here that this is momentum is h over lambda prime. So this is h over lambda prime. And if I want the x component of that, I have to multiply by cosine phi. This is the x component of the scattered photon's momentum. The x component. Now, what is the x component of the scattered electron's momentum? So I'm going to add to that plus, well, it's mass times velocity, right? So I can write me times gamma, c me times, so the moving mass is me times gamma, right? We know that. And if I take beta times c, that would be times velocity. So this term right here is the moving mass. This is the mass term. This is the velocity term. And then I need to take the projection onto the x-axis, and that becomes times cosine of theta. So I have equation 1, and equation 2 is the x component. Okay? So these are two equations. This is conservation of energy. This is conservation of x component momentum. All right? Got one more equation. Good? Okay. So finally, I've got the y component momentum. And the y component momentum says that initially, there is no y component of momentum because the photon is moving in the x-axis. So before I have 0, and afterwards, the y component of the photon's momentum is going to be equal to h over lambda prime times sine phi. And then I'm going to the recoil electron. Notice that if the photon gets a y component in the upward direction, the electron has to have a y component in the negative direction because the two have to balance because it was 0 before. Right? 0 before is equal to the sum of these two, and those components have to add up to 0. So I get the same thing, which is me times gamma times beta times c times the sine of theta. And that's equation 3. Okay? So, let's see what I've got in terms of equations and number of variables. My variables in this, so I have lambda prime, are clearly variables that are in here. I have velocity v, which is equal to beta times c. This is for the electron. So I have the electron velocity, that the electron recoil velocity. That's clearly a variable. And then I have another one, which is, well, I guess you could say two more. I have the scattering angle phi and the scattering angle theta. Let me take lambda as a given. Let's suppose that lambda, we'll say this one is equal to a constant. So let's say this number is given, right? We're given the incident photon wavelength. Okay, that means that now I have 4 unknowns, lambda prime, v, phi, theta, with 3 equations to relate them. So clearly I cannot solve for a unique value, because I need to get a unique value, I need 4 equations, 4 unknowns. Right? I have 3 equations and 4 unknowns, so I can eliminate 2 of the variables by doing that. And the variables I choose to eliminate are, theta and velocity, or we say v of the electron, right? I want to eliminate those 2. I could do, of course, I could choose a different combination, but because this turns out to be the most useful form, we're going to eliminate the angle and velocity. I can show you very simply one way you get rid of these angles is notice that if I isolate the cosine theta, take this term on the other side, I have a sine theta, and I bring this term on the other side, and I square them and I add them, I get a sine squared plus cosine squared. That adds up to 1. Right? So that's right away one way I can get rid of one variable. Right? And from that, I can then use the resulting equation with one other equation, like energy conservation, to eliminate the velocity. Now, there's a derivation in the book. People complain about long derivations and a lot of algebra. So I'm going to give you the answer, which hopefully is what you might want to use anyway. So we will go to that and simply say that by eliminating the theta of the electron, so notice I'm eliminating the electron variables. Theta and V are both for the electron, right? So I do this for the electron, and I get that the result after a significant amount of algebra is the equation has become known as lambda prime is equal to, became known as the Compton scattering equation. Lambda prime equals lambda plus h over the mass of the electron times c times 1 minus cosine of phi. Right? And the way so what we have done basically is to say, as the angle of the scattering increases, as this angle increases, the photon wavelength will obviously change, but it will in fact get larger and larger because I'll be subtracting less and less as phi moves away from 0. And it predicts the correlation of this variable versus this variable. So experimentally, what I'm doing is if I want to measure lambda prime versus phi, okay? And or I could call it delta lambda versus phi, right? So I could say delta lambda is equal to lambda prime minus lambda. Okay? So if I plot this out and I do the measurement, then I should be able to get this is lambda prime minus lambda, and now this thing goes 0. Give me a second here. I'm going to plot out this quantity 1 minus cosine phi. It starts at 0 when I get to pi. So it basically is going to be 0, and it basically does this. And this would be 0 to 180 degrees. So this, and the height of this would be h divided by me times c. So the experiment can be done. The experiment can be done by measuring delta lambda versus phi. And the expectation is that we get a curve that looks something like this, which is a 1 minus cosine phi term. And in fact, that is in fact what happens. And the largest it can ever be, lambda prime minus lambda, is equal to h over MEC. Now this number is used so frequently that we can actually write it out, 243 nanometers. And this is a quantity that we use for calculations. Notice H is a constant, ME is a constant, C is a constant. I just plug it in and I get a value which is 0.00243. So this is the equation for Compton scattering, and the fact that it has been observed and it has been confirmed. And of course, the one who did this was Arthur Compton, so obviously that's why we call it Compton scattering. And what it basically shows is that we can consider the scattering of an X-ray off electron as essentially a billiard ball collision. This is essentially a photon, a particle of light, hitting a stationary electron. The photon comes off with a new energy because it gave some of it up to the electron. The electron gets scattered. This is the recoil electron. And it comes off with some of the energy, and this comes off with the rest of it. But the analysis is done as the scattering of one particle off of another. I could also, for example, consider the cue ball and the 8 ball. The cue ball comes in, hits the 8 ball, the 8 ball recoils one way, the cue ball recoils the other way, and this is in fact a billiard ball collision. It is a confirmation of the particle theory of light, and we get, in fact, a confirmation, third confirmation, that H is equal to 4.14 times 10 to the minus 15 eV seconds. Third experiment, third confirmation. H is a fundamental constant. When multiplied by the frequency of light, it gives the energy per particle of that light. And furthermore, it seems to be the same regardless of which experiment I use. So it's a fundamental property of light, not just a, not just a parameter that was fit for one experiment. Okay, so you have enough to get started. Well, after the exam on Tuesday the 5th, a week from today, we will work some examples of this Compton scattering and move on to the next section.